supply of actual material. But this is geologic material, it's rocks. And so you can fundamentally simulate many of aspects of rocks by mimicking the mineralogy, the texture, the particle size. And you've got the same problem for asteroid exploration as you do for lunar exploration. You've got meteorite types. You've got samples of the material that you're interested in. It's just that they're relatively rare and expensive and available only in small amounts. And if you want to start testing, you literally need tons of this stuff. And that simply is not available from the meteorite collection. And of course, there's a long list of science and engineering reasons for doing this. I won't go through all of them. Suffice it to say, almost anybody who develops hardware, tests hardware, and needs to validate hardware and procedures needs to do that in as realistic of an environment as possible. And the simulants help you create that realistic environment. So what to simulate? Well, actually, these are only the titles of big long sections in our simulant report about properties to simulate. Fundamentally, you want to try to get a simulant that is as representative of your eventual target as you possibly can. And what we're mostly focusing on are physical and chemical properties, so that you have a decent mineralogical and chemical simulant, particularly for things like in situ resource utilization, and also grain size, so you can handle and process more or less the same way. Source of data. Well, the nice thing is we have meteorites. We have pieces of rock that fall out of the sky and end up in our meteorite collection. So we have a good idea about the chemistry and the mineralogy. We have a good idea about the strength. We have a good idea about the particle size. You can also get other sources of data like observations of bolides, which tell you about the strength of the larger pieces. Observations of near-Earth asteroids, which again tell you about strength, the gravity environment, thermal inertia, so the existence of regoliths and the rough, basically the texture of regoliths. And so there's a lot of information available. So we start with meteorites. And of course, there are strong indications that meteorites fall out of the sky. And sometimes it's hard to ignore these facts. And the first thing you find in meteorite types is that there are something like 17 compositional types. These are the sort of large groups. And the range of mineralogy, looking at silicates versus metal, looking at strength versus and hydration state, they're highly variable. So there's a lot of information here to simulate. And the first thing you realize is that one asteroid simulant does not fit all. So it's pretty clear that you can't, that you're going to have to tailor your simulant to your target. What to simulate? Well, it turns out that there's a couple of factors here. First is that almost all the volatiles are in just a very few number of, small group of meteorites. That essentially, if you're interested in extracting water from asteroids, or if you want to go to an asteroid because it has mineralogically bound hydroxyls, that tells you where you need to go. The other factor to consider is that most meteorites are actually pretty tough. It turns out that carbonaceous chondrites are relatively weak, but some of them can be tougher than concrete. Ordinary chondrites are extremely tough. And I spent 5 years working with Dr. Peters here as her student. And one of the things I did was I mostly smashed meteorites. I have probably smashed more meteorites than anybody else in the meteorite community, and it's left me with it's earned me the lasting enmity of all the meteorite curators that I know. They're deeply suspicious of my motives. And I tell them I want to smash the meteorites. Anyway. So just remember that things like ordinary chondrites are extremely tough. And some of them are a factor of 10 tougher than concrete. And I can give you pieces of meteorite, and you can go and you can actually break concrete just fine with the meteorite, not hurt the meteorite much. And as I tell people, if you're interested in in situ resource utilization, there's no substitute for hitting meteorites with a hammer and learning how either hard or soft they are. So, and the nice thing is we have samples of asteroid regoliths. If you're a regolith accumulates solar, wind, and planet gases. And so these are all solar, wind, and planet gas-rich meteorites. And basically, they're telling us the texture, the mineralogy, the structure of a regolith. And most asteroids have regoliths. This is a thermal inertia of the moon. So this calibrates you on a level of dustiness. Most big asteroids are dustier, have lower thermal inertias than the moon, so are dustier than the moon. Smaller asteroids are less dusty than the moon. The regoliths are more granular and rough, but nowhere close to the pure rock, the bare rock value. So you've got some level of a mixture of boulders, cobbles, pebbles, and dust. So our approach is you look at the mineralogy of meteorites, and it turns out that most meteorites that are of interest for missions and in situ resource utilization are from a relatively few groups. And what they do is they repeat in varying amounts a suite of mineralogy. And so most of this is pretty straightforward. So our approach is to just stockpile that mineralogical feedstock and tailor the mixtures to the individual meteorite group being simulated. So typically, if you're interested in hydrated carbonaceous chondrites, the dominant mineral there is going to be serpentine with a bunch of olivine and magnetite, and then a mix of relatively minor constituents. So what we try to do is constrain maximization of a high fidelity simulant that's both safe and affordable for large scale engineering tests. And we try to get the chemistry and mineralogy, particularly the volatiles, very close to what we're trying to simulate in the meteorites. Another factor that's not very well acknowledged by the meteoritical community is that these meteorites actually have substantial toxic hazards. Now, the thing is that if you're a meteoriticist and you're working with milligrams or micrograms of sample, that's not going to hurt you. The death rate amongst meteoriticists is not different than the general population. But the problem is that the organic components, a big chunk of the organic components of the volatile-rich carbonaceous chondrites are actually banned in California. So the Sutter's Mill meteorite that fell in California actually contains things that are banned in any amount in California. So you could not legally sell this meteorite in California as a commercial product. And so that's okay for Sutter's Mill because meteorites don't care where they fall, but it is a problem for someone like me who wants to stay out of jail. So what I do is I don't put the type 4 kerogens, which are notorious carcinogens and mutagens, into my simulant. So you lose a little bit of fidelity, but you gain a lot of safety. Same story with serpentine. Most serpentine polymorphs are quite safe. But serpentine is, forms of serpentine do contain asbestos. Some contain lots of asbestos. Turns out that the volatile-rich carbonaceous chondrites do contain a lot of asbestos. Again, if I tried to ship the simulant across state lines with high fidelity for the morphology of the serpentines, I would get into trouble. So I don't do that. Talcum, Johnson's baby powder has more asbestos in it than these simulants. And it's actually easy to tell the good serpentine from the bad serpentine. That is the bad serpentine. This is the good serpentine. You know, if it doesn't have an asbestos form, you're okay. So input materials. These are just what you get inputs for our first simulant, which is based on a CI carbonaceous chondrite. And this is the output right here. As you notice, a little bit of dark material goes a long way to making the final product dark. And actually the results were pretty good. That's the simulant. That is a volatile-rich meteorite. The mineralogy, the texture, the albedo, the volatile release patterns were pretty good. Strength, density, and porosity were also pretty good. The general handling, this stuff is really dirty. I have samples if you would like to take a look, close look. Be careful. This is being used by several ISRU operations already. And I will just go to the final slide, which is phase 1 was doing CI-like carbonaceous chondrites. We substituted pyrite for trolite and peridotite because there is just this tiniest explosion hazard. And so, you know, we're trying to make this safe. In phase 2 with Deep Space Industries, we are producing CM-like, Tagish Lake-like, CR-like, CV-like, and ordinary chondrite-like simulants. And if you're interested in any of this, give me a call. Thank you.
Hi, Dan. When you produce the simulant, does it come out of the oven or something as a rock, and then you grind it to a powder, or do you produce a powder that then you compress into a rock?
We produce the powder, and there are a couple of ways that you can make it into the rock. It turns out, I didn't go into this, but smectite is actually a wonderful cement in these volatile-rich carbonaceous chondrites. And that's probably what holds it together in space. And so varying the amount of smectite by a small amount, we can actually reproduce the whole range of carbonaceous chondrite strength properties. So we can provide it as a rock, or we'll provide it as a powder and you can make the rock. Well, we have instructions for that. And actually pressing doesn't work that well. We've tried.
Pam Clark, JPL. I have a question about the processes you're using and whether or not you make any attempt to, I mean, we have a essentially chemical compositional analog,
yeah.
But you make any attempt to make surface properties that would be likely would anticipate on asteroids?
Well, what we do is we follow what we see in particle size in the meteorites.
Okay.
And the surface properties, for instance, the textures, we can duplicate those with the relative ratio of rock to dust. And it's easier to make these things into the rocky form. But that really is something that we'd have to work with the potential customers on trying to get the